Yeah, Bismillahirrahmanirrahim. We continue our lesson today with the prime and grade common divisor or GCD. Yeah, first of all, what is the prime? The prime number is a natural number, is greater than 1. Is a prime number is a natural number that greater than 1. Natural number that greater than 1. It is not the product of two smaller natural numbers. Natural number greater than 1 is not a prime number, it's called a composite number. Okay. Okay. And then we have, for example, 5 is a prime because the only ways of writing uh, uh, a product is 1 multiplied by 5 or 5 multiplied by 1. For example, we have 5 multiplied by 1 and 1 multiplied by 5. Okay, and then we can conclude this one, 5 is a prime number. Okay, the other prime number that less than 100, you can list. For example, you have 2, you have 3, you have 5, 7, 11, 13, and so on. Okay, until 89 and 97. This one is the prime number. Okay, do you have any question so far? Is it okay? Elewatan boleh ke? Okay, and then this is just further explanation. It is a positive integer that must be greater than 1. It's called prime if the positive factor of p are p and 1. Okay, and then a positive integer that is greater than 1 is not a prime. For example, we have 4, 6, 8, 9, 10, 12 that can be divided by 2. We call it as a composite. And then the fundamental theorem of arithmetic is every positive integer can be written uniquely as a product of prime, where the prime factor are written in order of increasing size. For example, if you have the prime factor of 15, uh, we can define as 3 multiplied by 5 or 5 multiplied by 3. Okay, for 48, we can multiply 2 by 2 by 2 by 2 and multiply by 3. Or we can do power of 4 multiply by 3. Okay, okay. Or you can write like this. 48 equal to 6 multiplied by 8. And then 2 multiplied by 3. And then you multiply by 2 power of 3. Okay, and then 2 and 2, 2 power of 4 multiplied by 3. And this one is, we call it as a prime factorization. Okay, this one is prime factorization is very is a way or expression of expressing a number as a product of its prime factor. Prime number is a number that has exactly two factors. Number one is a number of itself, and for example, if we take 48, and then if we have here 17 is 17, and then if we have 100, we can have the prime factorization to power of 2 multiplied by 5 power of 2 lah. Okay, if you put the prime factorization like this, 100 and then is 10 multiplied by 10 equal to 2 multiplied by 5. Okay, multiplied by 2 multiplied by 5 lah. Then we have a 2 power of 2 multiplied by 5 power of 2 lah. Okay, because here we have 2 1 and 2, here we have 1 and 2 lah. Okay. Okay, so far do you have any questions? Is it okay? Hmm. Number one, so far dia tak ada. Dia mesti ni number, it must be integer. Okay. Okay, kalau contoh, for example, another example, we have 72. 72. We can use like this, 4 multiplied by 18. Okay, and then here you can 2 multiplied by 2, and then multiply by 3 multiplied by 6. Okay, and then prime factorization. We have 2 to 3 power of 2. Okay, okay, and then we got 2 here, 2 multiplied by 2 multiplied by 3 multiplied by 2 multiplied by 3. Then we got 2 power of 3 multiplied by 3 power of 2. This is a prime factorization of 72. Betul ke? 2 kali 2, 4. 4 kali 2, 2 kali 2, 4. 4 kali 2, 8. 8 kali 9, 72 lah. This one is prime factorization. Okay, is it okay? Boleh ke? Boleh. Another example, if you got 48. Another example. Okay, if you have 48. Equivalent to 8 multiplied by 6. Okay, we got 4 multiplied by 2 multiplied by 2 multiplied by 3. And here we got 2 multiplied by 2 multiplied by 2 multiplied by 2 multiplied by 3. Then we got 1 2 3 4, 2 power of 4 multiplied by 3. Okay. Okay, and then 2 power of 4 multiplied by 3. This one is we call it as a prime factorization. Okay, if n is composite integer that is not a prime number, then n is a prime divisor less than or equal to power of n lah. This is easy to see if n is composite integer. If it has two divisor P1 and P2 such that P1 multiplied by P2 is equivalent to n lah. And P1 is must be greater or equal to 2 and P2 is must be greater or equal to 2. And then P1 and P2 cannot both be greater than the power of n because the P1 multiplied by P2 would be greater than n. If the smaller number of P1 and P2 is not a prime itself, it can be broken up to prime factor that can be smaller than itself but must be greater or equal by 2. So we have greatest common divisor, or we can call it as a GCD. Uh, GCD let A and B be the integers, but both A and B must not be 0. And then the largest D, such as D A and D B, is called greatest common divisor of A and B. Okay, this one is common. We have D can be divided by A, D can be divided also by B. Okay, and then the greatest common divisor GCD of A and B is denoted by GCD AB. Okay, for example, we have GCD 48 and 72. Okay, and then the positive common divisor of 48 and 72 are, okay, we have 1, 2, 3, 4 until 16. And then we have 24. So GCD of 48 and 72 are 24. Is 24. Okay. Okay, what is GCD of 19 and 72? And what is GCD of 45 and 60? Okay. Okay, another example. Okay, we have GCD for 24 and 36. And 36. Okay, okay, for 24, okay, we have 1, 2, 3, 4, 6, 8, 12, and 24. And for 36, we got 1, 2, 3, 4, 9, 12, 18, and 36. Okay, we can see that greatest common divisor for both 12 and 36 is 12. Okay, this one is by listing. This one we listing. Okay, and then we have factorization. Factorization. We have 24, 36, 2, 12, 2, 6, 2, 3. Okay, and then for 36, 2, 18, 2, 9, 3, multiplied by 3. And then for prime factor that are common, we have 2 GCD, 2 multiplied by 2 multiplied by 3 is equivalent to 12. Okay. Okay, this one is we can use the factorization. Okay, and then the other one, okay, we can use the GCD using the repeated division. Okay, we have GCD with 2, 24, and 36, 12, 18, 2, 6, 9, then 3 lah. Then the GCD is 2 multiplied by 2 multiplied by 3. Okay, is equivalent to 12. Boleh eh? We have 3 ways eh. First, we go by the listing. Secondly, we go by the factorization. And number 3, we go by the repeated version. Repeated division eh. Okay, and then to find the GCD and LCM for the pair numbers for A and B, we got division operation, prime factorization, and Euclidean algorithm. Okay. Okay, for the division operation, this one is okay. I will explain. For 48 and 72, we have 2 multiplied by 3 multiplied by 4. We got 24 lah. Okay, and then for LCM, we got 48 and 72 for the M. Okay, we got 2 multiplied by 3 multiplied by 4, and then we got the here 2 and 3 multiplied by 2 but multiplied by 3 lah. We got 144 lah. Okay, least common multiple. Least common multiple is the lowest common denominator that can be calculated in two ways. Here we can calculate by using the division operation or prime factorization. Okay. So far, do you have any question? Okay, and then for the another example is 48 and 72. Okay, we have this one for the prime factorization. Okay, this one I have explained earlier. Okay, we have 48, 2 multiplied by 3 multiplied by 2, and 2 multiplied by 4 multiplied by 3. Okay, for the minimum, okay, 72, we have 2 multiplied by 3, 2 multiplied by 4. We got the minimum here. Okay, 2 multiplied by 3 multiplied by 3 power of 1. Okay, and then we got 24. Okay, we got the minimum for GCD. For the LCM, okay, LCM least common multiple. we got max. Max 2 power of 4 multiplied by 3 power of 2 lah. Then we got 144. Okay, 3 power of 1 lah. Okay, okay, we select this one and this one lah. Okay, and then using the prime factorization, GCD can be computed using the prime factorization of A and P lah. Okay, we have GCD P1 minimum, P2 minimum, Pn minimum. Okay, and then for example, we have GCD 60 and 54. Okay, we list out the 2 power of 2, 3 power of 1, 5 power of 1, and then for 54, 2 power of 1, 3 power of 3, 5 power of 0. We have 6. Okay. And then for GCD A and B, okay, we find this one 2 power of 1, 3 power of 1, and then 5 power of 0. We got 6. Okay. 2 multiplied by 3 multiplied by 1. Okay, we got 6. Then for least common multiple, LCM, the positive integer for A and B is a smaller positive integers that can be divisible by both A and B. Okay, for example, LCM for 3 and 7 is 21. A and B is M. Okay. Okay, do you have any questions so far? Is it okay? Okay. Okay, LCM stand for least common multiples. LCM. Okay, for the LCM, we list out the max. It's different from the GCD. We go for the minimum. Okay, for example, we have P1 max, A1, B1, P2 max, and so on. Okay, for A is equal to 60. We got a 2 power of 2 multiplied by 3 power of 1, 5 power of 1, 2 power of 1, 3 power of 3, 5 power of 0. And then for the LCM, we go for the maximum, 2 power of 2 multiplied by 3 power of 3, okay, multiply 5 power of 1. Here we got the maximum here. Okay, and then we got the 550. Okay, 4 multiplied by 27 multiplied by 5 equivalent to 540. Okay, then exercise find the greatest common divisor of these pairs. Okay, we have this one. Please do in the Padlet. Okay, this one please do in the Padlet. Okay. Okay, and then we have relative prime integers. Two integers and such as a and b are relatively prime if GCD a and b is equivalent to 1. Okay, for example, 15 and 28 relatively prime? Yes. Okay. Are 55 and 28 relatively prime? Yes. Are 35 and 28 relatively prime? No, because GCD 35 and 28 and are equivalent to 7. Okay, in mathematics, two integers a and b are we can call it as a relative prime when there are no common factor other than 1. Okay, 17 and 22 are relatively prime. Is it relative prime or not? The answer is yes. Lah. Okay, because GCD for 17 and 22 are equivalent to 1. Lah. Okay, relatively prime, yes. Lah. The answer is yes. Okay, the definition of relatively prime are pairwise relative prime if GCD AI and AJ is equivalent to 1, whereby the 1 is I is less than or equal to 1 and less than J and less than or equal to N. Okay, for example, if we have 15, 17 and 27 are pairwise relatively prime, the answer is no because GCD 15 and 27 are equivalent to 3. Okay, 15, 17 and 28 pairwise relatively prime. Yes, because the GCD of 15 and 17 are equivalent to 1. GCD 15 and 28 is 1 and GCD 17 and 28 also 1. Lah. Okay, then the answer is yes. Lah. Okay, this one is no. Okay, this one please do in a Padlet for the exercise for this one. Padlet. Okay, and also for this one. Okay, this common this common multiple. Okay, you do the maximum. And then the relationship between GCD and LCM. Okay, we can find the GCD is for the minimum and LCM for the maximum. Okay, then the theorem A multiplied by B is equivalent to GCD A B multiplied by LCM A and B. Lah. Okay, and then if you got to conclude that we can find out this number is equivalent for the theorem A multiplied by B. Lah. And then for the third one, we got the Euclidean algorithm. The Euclidean algorithm find the greatest common divisor of two integers a and b. For example, if you want to find the GCD of 287 and 81, we can divide 287, the larger number, by 91, the smaller one. Okay, and then okay, okay, 287 is equivalent to 91 multiplied by 3 plus 14. 270 minus 91 multiplied by 3 is equivalent to 14. 270 plus 91 multiplied by negative 3 is equivalent also by 14 lah. If we know that for the integers a, b and c, if a can be divided by b, then a also can be divided by b and c multiplied by c for all integer of c lah. Therefore, any divisor of 91 is also divisor of 91 multiplied by 3 lah. Okay, you can divide. Okay, in mathematics, the Euclidean algorithm is an efficient method for computing the greatest common divisor of two integer numbers. The largest number that can divide them both without a remainder. When that occurs, there are GCD of the original of two numbers. Okay, and then we got the algorithm to represent the Euclidean algorithm for 287 plus 91 multiplied by negative 3 is equivalent to 14. We also know that the integers for a, b, and c, if a can be divided by b and a can be divided by c, then a also can be divided by b plus c lah. Okay, therefore, any divisor of a of 287 and 91 of b must be also be divisor of a. Okay, so we can conclude that 287 plus 91 multiplied by negative 3, which is 14. Okay, this one I explained. Consequently, the greatest common divisor of 287 and 91 must be the same as the greatest common divisor of 14 and also 91. Okay, GCD 287 91 is same by the GCD 14 and 91. So the Euclidean algorithm, okay, 14 multiplied by 6 plus 7, that means that GCD of 14 and 91 is 14 7 lah. So we divide 14 by 7, we got 0 until the remainder is 0. Okay, we find that 17 also can be divided by 14, and thus the GCD of 14 7 is equivalent to 7 lah. Okay, this one is Euclidean algorithm. 200 2875 by 4915 is equivalent to 5. Okay, we divide by the smaller divisor and a large dividend. Okay, and then 2075 to 050 plus 875. Okay, 2. Okay, and then the last one is remainder of 0. Okay, this one is Euclidean algorithm. Okay, this one is for the LCM. Okay, we divide by 5 lah. Okay, we got the LCM 2,875 can be divided by 4,915 for the LCM and GCD by the using the theorem A multiplied by B is equivalent to GCD A B multiplied by LCM A B lah. This one is Euclidean algorithm. Okay, so this one 5 lah. Okay, we got this one by 5. Okay, and 0. Okay, so okay, this one 2,875 and 4,019. Okay, this one divide by 5 is equivalent to 2,827 26,125. Okay, for 24 as GCD 48 and 72. For the LCM we got the maximum. Okay, so here okay 48 multiplied by 72 GCD 48 72 48 and 72 we divide by 24 lah. Okay, and then divide by 24 we got 144. Yeah. Okay, this one is another example. 2,875 915 is equivalent to 5 lah. Here we divide 915 to 175. Okay, and then we got we continue until the remainder is 0 lah. Okay, 915 3 plus 130. Okay, and then 130 here 7. Okay, plus 5, and then here 5 multiplied by 26. Okay, plus 0. 0 is the remainder. Okay, this one for the 1,221 and 144,030 for the divisor and dividend. Okay, we have like this. Okay, we got 1. Okay, okay, plus 999. Okay, and then we continue here 222 here multiplied by 4 111 until 0. Then for the GCD here we multiply by 111. We got 158,730. Okay, this one is another example using the greatest common divisor 414 and 662. Okay, this one can be done using the computational programming as shown in the next slide. Okay, we let A equal to B, Q plus R, where A, B, Q, and R must be integers. and then GCD AB, GCD BR. Okay, this one for the Euclidean algorithm in the pseudocode. Okay, in the pseudocode, you can see the procedure for GCD AB must be positive. Okay, we 15 mod by 3 is 0. Okay, the syntax is modulus. Okay, multiply, start for multiply here as a power. Okay, divide. Okay, x equal to a. This one we initialize. Initialize, and y must not same as 0. And r equivalent to x mod by 1, y, x equal to y, y equivalent to r. And then n for the x is GCD A and B. Okay, for this one, for the 12, 18, 111, 201, GCD 1005, 040, you can upload to parallel. Okay, this one for the LCM. LCM, we have the LCM for the 1,221 and 144,030, 14,430. Okay, we go here 222 until we got 111. Okay, we start from here 111. Okay, this one for the GCD, this one for the LCM. Okay, 144 minus 100, 1,221, 11. Okay, this one 1 minus 222 multiplied by 4. Okay. Okay, and then we divided by 111. Okay, this one is a application of theory number. We have Bizot theorem. Okay, if we have A and B are positive, then there exists S and T such that GCD A and B. Okay. Okay, this one is for S and T. Okay, for the Bizot identity is defined as if A and B are two integers and D is their GCD. Okay, then this one is example. Okay, okay, express the GCD for 252, 198 is 18. Actually, a combination of 252 and 198. Okay, okay, this one is step by step for the Euclidean algorithm. Okay, 1 multiplied by 198 plus 54. Okay, this one for the GCD, 54 is equivalent to 252 multiplied by 1 multiplied by minus 1 multiplied by 198. And then we multiply by okay, and then we got 36. Okay, we got 18. Okay, and then this one for the exercise. This one you can go for the answer. This one is the answer. Okay, we go by the next exercise. This one for the number theory and Euclidean algorithm next week.